Hello guys, welcome to Backbencher Studies channel. In the last video, we discussed how the frequency response of a second order system can be analyzed based on the normalized frequency of this system. So we already saw that the magnitude of the transfer function, how it will be varying with respect to the normalized frequency u and the damping factor delta over here. And we saw that the angle or the phase of this second order system is also dependent on the normalized frequency as well as the as well as the damping factor of this second order system over here. So let us move on in this session by finding out the magnitude and phase response of a particular system with varying frequency over here. So if this is the graph showing how the amplitude or the magnitude of this or system varies with respect to the frequency over here. So on x-axis we are taking the frequency. So with increasing frequency, this is how the magnitude of the system varies. The magnitude response of the system varies, which is the magnitude of the frequency response. So if we so this is plotted with respect to the normalized one. So we have what is called the normalized amplitudes over here, which is 1 on 0.707. So if we are observing that for varying frequencies we have what is we called as increasing for lesser frequencies we have increasing amplitude. This can be depicted because the frequency is varying with a little amount, so it the magnitude will be increasing not indefinitely but up to a certain extent, and at the extent the threshold value up to which the frequency, that frequency what we call as resonant frequency. So resonant frequency is where we can get the maximum of the magnitude of the frequency response, and this value, the amplitude value, that is what we call as resonant peak MR. And if we are going beyond these resonant frequencies, then we can have something decreasing amplitude with increasing angular frequency omega. And if for particular value of this 70.7% of the zero frequency value, we have what is called the bandwidth. So these are some characteristics of the frequency response over here. So let us derive these characteristics based on the equations what we have derived for the magnitude and phase. So this is a typical second order system with natural frequency omega and damping constant delta over here. So finding out the frequency response, we substitute s equal to j omega in our transfer function equation. So this is what we have. We did this in last session. So minus j omega square, j square will be minus 1, so we have minus omega square plus 2j delta omega into omega n plus omega n square. So if we take out omega n square from denominator, then we have 1 minus omega square by omega n square. This omega square is written over here, and this 2 delta omega n will become omega by omega n. And if we replace this omega by omega n, which is the normalized frequency, then we can have this kind of magnitude and phase response in terms of the magnitude, in terms of the normalized frequency. So this is what we already saw. So for deriving the resonant frequency, what is resonant frequency, we need to study. So we already saw that the resonant frequency is the frequency at which the maximum value of the amplitude occurs. So if we find out this derivative of this function with respect to the frequency, then we can, and if we equate that to 0, then we can have the resonant frequency. So differentiating the magnitude response with respect to the normalized frequency u, we have, so we have 1 by x to the power something over here, which is x to the power minus n. So if we differentiate that, we have minus n into x power n minus 1 as our answer. And if we do that, then we have minus half, and as it is minus half, we have this term which is in the denominator, whole to the power of minus half minus 1, which gives us the minus 3 by 2 term over here. And if we do the internal differentiation for this, we have the internal differentiations as we have x square as the derivative. So the derivative of x square will be 2 into x, and if we do that internal differentiation again, then we have minus 2u, which gives us the derivative of this minus u square over here. And if we do this differentiation, then we can say that this is giving us the 4 delta square u square. If we differentiate that u square with respect to the u, then we can have 2 delta u into 2 delta. So that is what we are getting with internal differentiation. So if we equate this, if we solve that and equate that to 0, then we can have the resonant frequency. So by equating this term to 0, then we can have this equation over here can be equated to 0. So if we do that, then we can find out the resonant frequency. So that's it for today, guys. In the next coming lecture, we'll be solving the other resonant peak as well.